Hello everyone, welcome to another problem session. So today we have another standard problem. There's a metal ring and it's attached to some other things. You can rotate this ring, and there's a magnet. So in the back you can say a magnet is north pole this way and south pole this way, and so these are the lines coming out. So these are the B fields, lines coming out from the north and south, from north to the south pole. So this magnet thing is fixed and assumed to be uniform, and this ring is going to be rotating at a constant angular velocity omega. And this is the height of the ring. Along this direction is h, along this direction is w, and we are supposed to find a couple of things. First, there will be an EMF induced in this ring. So we're supposed to find what the EMF will be, what the formula for the EMF will look like. That's using Faraday law, right? And then we're supposed to find the induced current in this. Current can go this way or that way, or maybe sometimes go this way and sometimes going that way. So we find that both magnitude and direction. Okay, formula for that and a statement for that. If the ring as a whole has a resistance R. Okay, so this will be kind of like circuit with an induced EMF in it. And because this is going to be all steady, we can just use a very simple Ohm's law to get the current magnitude, right? And for the direction, we'll see what the direction looks like. We are trying to use Faraday law to get the direction. So here the direction will be, if the electric field is that way in the wire, if electric field is that way, then the current is in the same direction. Okay, so if I know the electric field direction, we know the current direction. Okay. The last one is when you're rotating, you have to be doing some work, and you will see that how much work needs to be done by this external agent you can obtain from this. All right. So this is usually not asked in this kind of problems, but I thought that could be an important problem to ask. Another question related to that will be this ring will actually warm up so we can ask what's the rate at which the ring is warming up. Okay. So that's another extension of this problem you may want to think about. Maybe you talk to your friends, your teacher, what have you. So that's maybe you want to try to attempt this problem, and I will erase some of this and get myself some space and try to show you how I would do it. There are several ways of doing this kind of problems, and I'll just do it using Faraday law directly. Okay, to find induced EMF, what is induced EMF in Faraday law? In Faraday law, induced EMF is defined to be minus actually EMF is this integral E dot dl. That's the definition. And Faraday law says that this is equal to minus d dt of, if this is a oriented loop C, then this area of that loop, this integral b dot n hat dA. So this is actually what also called magnetic flux. And we can say phi b. This definition. So the rate at which the magnetic flux is changing. If it's not changing, just magnetic flux itself is not enough. It's rate at which. So the right side, I've been trying to say that the right side can be written as like minus limit delta t goes to 0, just for any derivative delta t, and we get the flux n hat dA at some time t plus delta t, subtract out the flux b dot n hat dA at t. So it's much easier to think in this language than that language, because we can actually set this up more easily. Okay, so this minus will cancel this minus. The EMF will be just this part. All right. So if you want to erase all this, then just erase all that, and then you can put a minus sign over here. Minus sign over here. All right. I hope you understood that. Okay, so we're going to do that. Over here, how do I get the magnetic flux? Well, this is oriented, so I will need to know what the n hat directions are. So for this, I need to pick the C, and because the magnetic field is coming out, we use the right-hand rule. So I'm going to pick a loop which will coincide. Loop will coincide with where the bar is currently, and it's going to go this way. So do right hand. So inside this area, you can see that I have, let me write down, draw it out. So the 90 degrees to that, let's put another color, choose another color like this. So this is the n hat direction, and I'm just looking at in the XY plane. So it's better to draw the XY plane. This is the X direction, and this is the Y direction, the XY plane. So B is in that direction. B is in that direction. That's the direction of B. The normal, the way I have drawn it out, is just in that direction. So that phi in original diagram is not correct. So this is the direction of the normal at this time, at time t, because when it rotates, the normal will point a little bit different direction. So this well, let's see at t equal to 0, it was like this. Assume n hat at t equal to 0 was in that direction. So it's rotating around the z-axis. So it's going to point in direction in this way. So this will be simply omega times t. So I choose t equal to 0 when n hat was the same direction as b. Okay. So this is my choice. So at this time there will be some flux. So this will give me some integral over here. So let's see what that will be. B dot n hat. N hat is a normal, unit normal. That's going to be b time n hat 1, right? This is bn, cosine angle between them, and there's cosine of omega t. So this is just going to be b, this is 1 cosine omega t. what is the dA? dA is the area of this loop, and that's let's see if I can integrate it. So over area A, B cosine omega t dA. Now this whole thing is independent of the area element. It's the same for that element, same for that element, same for this. So area element. So this comes out, and this is just a B cosine omega t dA, and this is just an area of the loop, which is B cosine omega t times length times width, the area, this rectangle. And so that's the answer for this part. Okay, let me pause. Okay, so we got that, that's equal to that. How about a little bit later time, n hat is pointed that way, t plus delta t, and so this angle now is omega t plus delta t. So all of this formula will go through. So the integral of this guy, b dot n hat dA at t plus delta t, will be identical to this, except t will be replaced by t plus delta t, bl omega cosine omega t plus delta t. And we're interested in delta t go to 0, so let's can expand this. So this will be bl omega. So you can do it a couple of different ways, and a simple way is just cosine omega t cosine delta t minus sine omega t sine omega delta t. Okay, so in the limit that we can see, this will be 1 minus omega square delta t square over 2, and this would be maybe omega delta t. Okay, so when you put in there this thing, limit delta t goes to 0, this first term, this one term, I mean this one term will cancel that guy from here, and you should work this out. So this will just simply be minus cosine omega t and minus cosine omega t times omega square delta t square over 2 minus sine omega t omega times delta t divided by delta t. So over here, this is the only one that's going to survive, and that's just going to be equal to minus sine omega t times omega. So that's one way of doing this. Another way, just over here, you just do a Taylor expansion, and then you'll get this. Okay, so let me erase this and try to clean up. Okay, so this is the answer, just copying it from here. So the EMF is actually, say this thing is, look at a time when this is positive, sine omega t is positive. So say there was a time, initially let's look at what's going at t equal to 0. At t equal to 0, this is b and this is n hat, t equal to 0. And then at that point you have a maximum flux. So max flux at that time, right? Because everything is together. So now at a little bit later time, this guy is rotated a little bit more, maybe. So it's over there. B is the same way, but n hat is now this way, a little bit off. Then so this is n hat at delta t, and this is at 0. So what's happening at this point is flux actually decreased. Flux actually decreased. So if you look at this integral with this, so this should seem, if sine omega t is positive, so this is t when this is the case here for t equals to delta t. So in that case, what's going to happen is E will be in the same direction as dl, and dl was going up here, so electric field will be going up, and the current will be, induced current will be in the same direction. So if the induced current is in that direction, that means it's going to induce its magnetic field. So this will be induced magnetic field. An induced magnetic field is in the same direction as the original magnetic field. It kind of adds to that original direction. So it's a induced magnetic field, not nearly. Induced magnetic field, you can say, is it has a little bit of x component and a little bit of x component, a little bit of y component. So it's got both x and y component, but x component is positive, which adds to the original magnetic field. So that means this flux was decreasing, is trying to restore the value. So this is B induced. B induced has a positive B induced X, since original B has positive BX. So they add to each other. So that just says trying to restore X direction flux through loop. So it's trying to restore that flux that was the original flux, which is decreasing. Now, when the loop has gone all the way, that is pointing in the other direction, you can see that loop was completely in the, not in the completely y, but was parallel to x. So suppose the loop was parallel to x, so here's the x-axis, and the loop was like that. Now the flux will be 0, and the next moment after that, there will be a flux coming out through the loop. So it will, the direction of the induced EMF will be, so there will be a time where omega t is actually going to be when t is such that sine omega less than 0, then this whole thing is going to be positive, and then at that point E will be opposite to dl. E will be anti-parallel to dl. That means current now other way, it's just going to opposite direction. So over here, just to make sure, current is going that way at one cycle, and if I am kind of like in that direction, then the current will be instead of going this way, in that this is A and B. No, this is C. AB, so it's like that. Now A, B, C, D. Now in that cycle, it's going to go this way. Current is going on to this way, and try to oppose the increasing flux through the loop. And this is what the what you have, what is called Lenz's law. But I want you to appreciate that the Lenz's law is actually built right in here. You know, if depending on whether this is positive or negative, you are going to have either electric field in parallel to DL or electric field opposite to the DL. All right. Okay. Let's see. Okay, so we done the A part. We've done the A part. Now we can try to do the B induced. The B is very easy to do because we have a EMF already obtained. We have EMF induced already got, and then we absolute value it, and then the resistance, that will be the magnitude of induced current. So this will just simply be omega B W L sine theta sine omega t, and we're just going to be absolutely, because we don't want to have negative here, the direction. And the direction we already talked about. Direction will be omega B omega L. This is all positive, so this is all positive. So this is just depending on omega t. So it depends on so there's a time such that sine omega t is greater than 0. Then the direction we have talked about is BC. In the BC direction, the DL is in that way. The DL is that way, and that means the electric field is that way. So, and if t is such that sine omega t is less than 0, that will that's coming from, you know, earlier discussion we had. This will be at some other time, not that time, and it's still BC, A, B, C, D, and then now the DL is that way. DL is still that way, but the electric field is that way, just the opposite of DL. Okay, let's do the C. Okay. Okay, so here we are facing with a loop of wire. The resistance is R, and take an instant at t where the current is going that way. We just look when sine of omega t is positive, right? So sine of so the current at this point is omega b, let's call this WL, let's call that area A, sine omega t over the resistance. Okay, so we are looking at really steady, very steady situation. So this is kind of like an AC current, right? If you look at this, this current is, so this is AC current situation, alternating current going back and forth. Sometimes current going this way, at some later time it's going this way when the ring is in another place. Okay, and EMF was I think it's looked like a sine omega t, no, EMF of cosine omega t. EMF was a minus cosine omega t. So this one is cosine omega t. So it's a, yeah, so EMF was when it's -0, it's kind of like this, yeah. It's so this is a situation. So power, you can show that the power P will be, because this is a purely resistive circuit, so purely resistive circuit. So we can just not look at whether it's there's a capacitance here or things like that, or inductance, you know. So we're not looking at inductance, capacitance, or anything, but those are there, but we're not looking at it. So power will simply be I square R. So when power that's dissipated will be power just that's going into this wire would be this is the work done per unit time by external agent. Now this power, if you look at the formula of the power, you notice something kind of interesting, that is I square it, I get a omega square b square a square, and it will be divided by r square times r, get a sine square omega t. So this actually depends on where I am in the cycle. If you look at power, it starts like this. So with time, it actually varies with time, and we can do a time average. So this will be some kind of time average. So let's do the time average. So this is what the time is. So this will be this time the time average of that. So power time average will just be this quantity, which let's call that P0, and sine is, so P0 is whenever this is 1, that's P0, right? That's, and sine square can be no more than 1, right? So P0 time average of sine square omega t time average. Now this quantity, what is the time average? So a time average is defined is take one period, because it's a periodic function, or two periods, a multiple of periods, right? You can have two periods, and you integrate to one period sine square omega t dt. So if you multiply by 2 here and 2 here, so you can do a double angle. Okay, so that will be 1 plus cosine 2 omega t. So over any number of periods, you know, this integral will give me 0, and this will give me just the period. So this is equal to actually 1/2. So this is equal to P0/2. So this, the answer will be omega square b square a square 2 times r. That's the answer. So this is the average amount of work per unit time you have to do in order to continue to rotate it at that rate. Okay, that's a good example. I will do a non-standard problem next in another video, in a separate video. Okay, so if you like this kind of explanations, please definitely like this button. Increases the visibility of this video to other users. And appreciate if you subscribe to this channel. You do get reminders. And then if you want to check out my website, where all these explanations are done out in much more detail, and there are many more examples for you to work through, and I think almost all the problems have solutions posted, so you can check your work against those answers. All right, take care. Bye.